Welcome to the final lecture of this week. In the previous lecture, we talked to you about the various properties of carbon nanotubes and why do you see such modulations in properties like electronical properties, mechanical, vibrational or thermal properties when you transform a planar structure like a graphene sheet to tubular morphologies. Clearly, you must have seen that significant changes in the properties are seen. If so, what is the use? That is the next question which we always ask. If there are changes in the properties, then where can those points be utilized? So, let us discuss today some of the applications of carbon nanotubes. In today's lecture, we will see some of the important applications. I must state right here that these are a selected few applications which are being discussed. In no way they are comprehensive overview of all the applications where CNTs are being utilized, because it is practically impossible to cover all the applications where CNTs are being utilized now, or it is proposed that they would be utilized in future. Just to cover each of these topics would require dedicated lecture courses. So, we would keep them brief, give you an overview and relate the applications to what has been taught till now in this course, so that you can understand the reasons why properties change in CNTs and how those changes are utilized to design and fabricate new devices. We will start from development of scanning probe microscopy and utilization of CNTs in this technique. We will talk about field emitters ranging from X-ray tubes to microwave amplifiers. Then there is a major area where these CNTs are being utilized, and they are chemical sensors. On the physical sensors type, we will try to discuss the case of flow sensors, and then finally we would see CNT based actuators and what is the working mechanism. We had seen in the first 3 lectures that the mechanical, electrical, magnetic and optical properties of CNTs can be tuned significantly as we go from different combinations of chiral numbers n and m, and you can have further modification in these properties if you go from single walled carbon nanotubes to multi walled carbon nanotubes, and then various arrangement of these structures. This is the reason why these structures which are based on carbon are finding large number of applications. One of the very interesting application is in scanning probe microscopy. So, what is an SPM? SPM is used to determine the surface morphology of a sample. Now, if this is the surface, I have to scan the surface and then move along, and as the morphology of the surface changes, that signal, if it is collected, it would give me the answer to how the surface is showing different kind of roughness or how smooth the surface is. So, if you see, you can have a surface, when you zoom it, it may not be smooth, you can have a rough surface, and this is typically the case. So, you have to have a mechanism by which you can collect the image of this surface. The scale we are talking about is in the range of angstrom or nano level. So, obviously, you cannot take a camera there and take a picture which can not go to such high resolutions. So, you have to modify your technique. So, what do? You take a cantilever, with a tip on the top, and now you move this cantilever throughout the sample, and when you get a trough, the cantilever can come down, and when there is height modulation, if the height increases, then the tip will move up and then cantilever will also move up. So, while monitoring the motion of this cantilever, you can draw the same picture on the XY plotter, and that will give you the shape and size of these crusts and troughs which are being observed on the sample. So, this is where carbon nanotube comes into picture. Question is, why it should be used? Now, you have a surface which needs to be scanned. So, you cannot use a very thick tip. Why? Because then it will not be able to measure this nano or angstrom level modulations. So, you have to have very thin tip. Now, if you take a metal and you have a very sharp tip of it, then it becomes very weak, and the moment there is a interaction with some kind of a obstacle or a hindrance, it will break, and then you will not be able to scan it. And that is where the mechanical strength of CNTs come into picture. So, when you take these tubular morphologies, they are very hardened structures. Their Young's modulus are very high. We had seen in the previous lecture that they are 6 times higher than that of steel. So, what do? You now use a MW or SWNT based probes. These structures are structurally robust, and they can also sustain tensile as well as torsional strains if they are there. But here you are just moving on the surface. First you will move x, then y, and then you have an xy movement. So, they can sustain these deformations without compromising their structural robustness, and meaning that CNTs will not undergo any permanent change in its structure even when it experiences external forces. Immediately you can then say that CNTs would become ideal for use as tips in such scanning probes. And the bending force, if you want to understand what is the compressional forces and the bending forces which can act on the tip, the bending forces are given somewhere of the order of 3I by r0 raised to the power 4 minus ri raised to the power 4 by 4L cube, and compressional force constant is given by Kc, where y is the Young's modulus, r0 and ri are the outer and inner radii respectively, and L is the length of the CNT. Now, because of high Kb, CNTs would be what? Would resist deformations against bending, and high Kc means the CNT tips will resist compression along their length and avoid deformation. So, you have both stability in the cross sectional view. If you look, you have in x direction, y direction, you have the stabilities. Next application which comes is in field emission transistor like structures. So, you can actually have a SWNT based FETs. So, you have a source, a drain and a gate voltage. This is a typical diagram which you see. Now, they are aligned channels, and this is what you need in FET, that there should be a channel for the flow of charge. And we had seen that the electrical properties in these channels can be changed by applying electrical and magnetic fields. This we had seen in the previous lecture. For this case, we will say let us consider on electrical fields. Now, if you look into the SWNT, they actually show ballistic or near ballistic transport with mobilities as high as 10 raised to the power of 4 centimeter square per volt per centimeter second. Semiconducting SWNTs exhibit ballistic or near ballistic transports with very high mobilities which are mentioned here. Now, because of these high mobilities, you can achieve high and faster switching speeds. And if you look into back gated SWNT FET, then the drain current which you will get can be changed by the gate voltage and resulting in high transconductance. What is the consequence? You can immediately have long channel FET operation with good conductance over micrometer scale length. So, you can have long channel CNTs and you can have good conductance over micrometer scale lengths. And the properties can clearly be controlled by controlling the defects of these CNTs. Now comes, if you look into the Schottky barrier height in such FETs and consider the thermionic emission model that relates the drain current to barrier height, you can find out that ID would be proportional to e raised to the power of minus phi b by k beta t. Hence, what you can clearly understand that by changing phi b you can increase IT, and the oxidation can also adjust SWNT electrode contact properties, and that can also change the value of ID. So, because of these flexibilities in parameters, CNT based FETs are becoming very important. You can get various configurations and you can have the plots of, let us say, log of channel conductance versus gate voltage, and you will find that if you compare with a typical MOSFET type structure, you can see that there is a significant change. Let us say at near point B, a kink appears which is not there in MOSFET. This is actually coming in because of the appearance of Schottky barrier at the source drain contact. And the 4 diagrams which are shown here, A, B, C and D, define the 4 regions: the thermionic emission region, the flat band conduction, the tunneling region and turn on region. So, the reason for change in these 4 regions is coming in because at very low Vg you have Fermi level which is near the middle of the Eg, and so current is mostly dominated by thermionic emission over the barrier height, and therefore conductance is low. If you go to the turn on region, that means you go to very high values of Vg, the device is fully on, the barrier effects are minimized and the current rises sharply. So, you have different regions in which different phenomena dominate, and hence you get different curves A, B, C and D points. You can now use, because there is a tip which we always discuss about in the formation of carbon nanotubes, you can clearly use these structures for making field emission electron source. Here the SWNTs can emit electrons at electric fields as low as 1 volt per micrometer. Why? Because of the sharp tip which you have. This allows you to have field emissions without the use of heating. That means it gives you the capacity for efficient cold cathode operation. and the emission follows the Fowler-Nordheim tunneling model, which is plotted here. So, you can see that by changing the value of V, you can get change in the voltage. So, you can clearly see that by just changing the values, you can get different currents which are there. And such capacities are making the SWNT cathodes a candidate for replacing thermionic filaments, allowing you to have cold cathode operations, enabling such systems to operate at low power. That means you need lower voltages. Hence, you can miniaturize the device, and you can also see that such systems, because they are very stable to temperatures, can also operate up to high temperatures. If you look into these systems even further, you will find that you can use such emitters and you can get various kinds of configurations which would maximize the emission efficiencies. So, you can have various types of configurations and you can then maximize the emission. So, you can go from single nanotube to random film to vertically aligned nanotube films to highly ordered arrays. Clearly, the emission capacities would be different. Hence, you will see that carbon nanotubes are used in emitters. For example, emitter in vacuum microelectronics. Why? Because you are getting the capacity to have cold cathode emissions. Therefore, you can make such systems which would give you the capacity to have very low heat generation, use of low power while maintaining the compact designs, and this is a typical sensor structure which is reported by the authors in a paper which has just been published. So, you can get very high efficient and temperature resistant X-ray tubed with sensors based on carbon. You can also make microwave amplifiers, and because of these ultra fast electron punching which is facilitated by CNTs, you can have improved amplifier efficiency, and this leads to reduced size, and the economics of such sensors or amplifiers are even in a way reduced that they are becoming cost effective. Then you can use them for space applications, for example, electric propulsion. Another example for emitters are in field emission displays. where each pixel has its own electron emitter that excites the phosphor to produce light. Such systems being also so robust, mechanically stable, also give you the capacities to have such displays which are highly stable and have long life. And we had seen their use in X-rays in the previous slides. Then comes the application of these carbon nanotubes, because you are changing the nature of the structure, the surface to volume ratio is changing and hence their chemical reactivity is changing, and subsequently you will find that CNTs are becoming extremely useful for a very important area, that is chemical sensors. And the sensing capacities are basically observed. Why? Because let us say you see a charge transport in a transducer, that is mostly electronic, but in sample it can be electronic, ionic or mixed. Now you take a CNT. This means you have taken asymmetric electron cloud distribution because of the curvature, making them electrochemically active through the rich pi electron conjugation. Now if you take an electron donating or withdrawing molecules, now you have some donating or withdrawing molecules passing near these CNTs. Let us say you are talking about NO2, NH3 or O2. These will interact with CNTs, hence they will alter the charge carrier of the CNTs and hence the conductance will change. And by measuring the change in conductance, you can find out what is the source of this change in conductance. And so CNT plus gas will give you certain amount of donor or acceptance or withdrawing ability, and delta will give you the amount of charge transferred. And you can also make flow sensors, because now you know that there will be interactions on the surface, so you can make flow sensors. And for example, you take the flowing liquid molecules and see how does the momentum transfer takes place, and then by measuring the change in voltage as a function of velocity, can you get some kind of a data. And this was done, and a linear relationship could actually be obtained. It could be predicted that the electric current and the flow velocity is linear, but actually the experiments showed a logarithmic voltage velocity dependence over nearly 6 decades. So if you see that experimentally you are expecting or observing a logarithmic voltage, whereas the predicted relation is linear, because the charge transfer mechanism is much more complex than what we can just model using a simple assumptions. For example, the flowing liquids with ionic contents would induce charge imbalance in the CNT, due to the shear deformation, and that would force deviations in the velocity gradient at the liquid solid interface, and hence the nature of the curve will change. You can also make electromechanical actuators, and you will find that applying, for example, voltage which injects electrons into SWNTs would now compensate the cations from the electrolytes. So, you have the SWNTs and now you have immersed them in NaCl. So, now what you have? You have a voltage. What will happen? That this voltage would be such that it would get compensated from the cations of the electrolyte, meaning that it would cause dimensional changes due to the quantum mechanical effects and band structure variations. And depending upon the expansion or contraction of these actuators, you can find out the sign of the charge injection. So, that gives you another way to just understand what is the charge which is flowing. If you want to make such a simple actuator, these are some of these steps. So, you have a CNT film is placed in a flexible substrate and immersed in an NaCl electrolyte. When you have at rest, then there is the condition of electrical neutrality. When you apply a voltage, what happens? It injects or removes electrons from CNT. Now, in an electrolyte, you have Na plus or Cl minus ions. These would move to CNT surface to balance the charge. Hence, you would see electronic doping changing the CC bond length. Now, when this bond length changes, either you will see expansion or you will see contraction. So, if you have a bilayer structure, one side expands while the other side will contract. So, one side will expand, the other side will contract, and then you will see a bending in the tube. And reversing the voltage reverses the motion, and AC signal produces oscillation. Finally, you remove the voltage and CNT returns to original shape because of its mechanical robustness. So, you can easily understand the nature of the charge which is injected. So, I hope you have now understood some of the applications of carbon nanotubes, and as we go along you will find that we will also talk about the use of carbon nanotubes or carbon structures in energy devices or few other devices which are finding large scale integration in today's scenario, and the carbon based industries are becoming extremely important. These are some of the references for your benefit. You can go through them to develop even more understanding. With this, we end the lectures of week 6, and we will start with a new topic next week. Thank you very much.